Thanks, Rob, and welcome. About 11 years ago, I had a performance issue, and I was drowning in profile data. I had to solve it by the end of the week, and by Wednesday, I thought, this is really not looking good. I had that bad feeling that I was not going to solve this one. After work, I played around with some visualizations, because I thought, maybe there's a way I can see the issue if it wasn't these 10,000 lines of text, if I could come up with a better way. I came up with flame graphs. I went to work the next day. I showed it to my co-workers. One of my co-workers, Isaac Schluter, he's like a younger version of Jeff Goldblum. At the time, he was the lead for Node.js. He looks at it and he says, that's too weird, it won't catch on. But Isaac is one of the kindest and wisest engineers in the industry. He played with it and tried it out, and after a few days, he changed his mind. And he told me, Brendan, I don't know how we did Node.js performance before flame graphs. It completely changed that industry. I went to Netflix, I got it going for Java and other runtimes, and now it's widely adopted. It's my privilege to share this with you. I'd like to begin by acknowledging the traditional owners of this land and pay my respects to elders past and present. My dream is to completely understand the performance of everything. The performance of applications, of libraries, of syscalls, the kernel, device drivers, hypervisors, firmware, and metal. Over the years, I've created various tools to aid with this. Latency heat maps have been widely adopted, flame graphs, methodologies, and lots of CLI-based performance tools. I'm going to talk about flame graphs. And flame graphs are really the one that's had the most performance wins, the largest monetary wins. It's primarily used to visualize CPU resource usage, but you can also use it for other things as well. I'll begin by showing you a quick tour of implementations so that you can understand that maybe you already have access to flame graphs because it's appeared in a lot of software so far. And then I'll explain what they are in section 2 with CPU flame graphs, show the challenges, and then go through advanced flame graphs. The takeaways: you will learn how to interpret CPU flame graphs wherever they show up, understand the runtime challenges, which is where most of the work has been. As I said, I coded flame graphs one night and came to work the next day and it was done. All of the work was making sure it worked properly in the JVM, in Go, in Node.js, and lots of other runtimes. And then why we need eBPF, a new technology for advanced flame graphs. The slides are also online, I should say. There's a lot of details here, but you can pull them down later. So the first section, a tour of some examples. I have more examples in a later section. This is also not an endorsement of any of these companies or products. It's showing you what's out there. My original version was 2011. I wrote it one night in Perl, and I'm not ashamed to say I love Perl. Seems a lot of people don't like Perl, but I love it. I write nice Perl. Some people write not so nice Perl. I really love it as a prototyping language, as I can knock things out very quickly, and then later on we rewrite them in C or Java or something else. So I prototyped it, it worked great, and I made it use SVGs or SVGs and JavaScript for interactivity. A few years later, my colleague at Netflix, Martin Spear, came up with a D3 version because I was talking to him about a problem with my Perl version was we didn't have so much live interactivity. We had some with the JavaScript, but I wanted to go further, and so Martin said, let's try D3. And now at the moment, a lot of usage in the world are either my old Perl version, because it just works and it's simple, or it's Martin's D3 version. But there's lots more versions. Just to give you a quick idea, Facebook were early adopters. They've got a version called Strobe Light. Node.js has lots of versions. I really like this one by David Mark Clements. It lets you there's these canned code searches to highlight different areas. Qt Creator was one of the first ones to include them in an IDE. Python vprof. This hasn't narrowed the color palette, so you have the angry fruit salad, lots of colors. Microsoft started adding them, so Windows Performance Analyzer for ETW traces. LinkedIn has a really great one they use internally, they've blogged about, which does differentials and other advanced features. Oracle added it to Developer Studio. Windows finally added it to Purview. Thanks Adam Sitnick and Vance Morrison for accepting that change. We've been pushing on that. Google, Martin, my colleague from Netflix, got it into pprof, which is used by a lot of things. There's a great one by Millian Wolf for Linux called Hotspot, which does off-CPU flame graphs, and it also lets you look at the disassembly from the flame graph. The Eclipse Foundation Trace Compass is this old analyzer that does a lot of things, and it's included flame graphs, so it's like a do-everything performance analysis tool. It's in Java Mission Control. At Netflix, later on, we created Flame Scope so that we can understand variants and perturbations that were otherwise hidden in flame graphs. I'll cover this a bit more later. We did a continuous profiler at Netflix called Flame Commander that did differential flame graphs. AMD has it in uprof, its analyzer. It's in YourKit. It's in IntelliJ. Firefox has a great one, profiler.firefox.com, where you can upload various profiles, and that does have flame graphs. Linux finally added it to the perf, which is the standard utility in Linux. So you can run perf script flame graph, and it will spit it out. Thanks, Andreas and Red Hat, for getting that done. It's in MATLAB, which kind of surprised me, but there you go. AWS has a service to sell it, CodeGuru to do optimizations. So does Google. Intel finally added to vTune, Intel's all-in-one deep analysis tool. It's in Splunk. New Relic has it, Datadog. Granulate has gprofile, an open source version that does continuous profiling and other features. Granulate's been acquired by Intel, so that's now an Intel product. Very recently, Microsoft added it to Visual Studio, and Grafana just added it to Grafana so you can incorporate that into dashboards. That's really great. I just went through a select few dozen, but there's over 80 implementations. There's over 400 related open source projects. I've counted at least 30 commercial products have included flame graphs. So far, there's 4 new startups that I know of that are doing flame graphs or flame graph-based tuning or continuous profiling. One of them has already had an exit. The amount of money that's been spent on flame graphs so far is over $1 billion Australian. I don't know how many end users there are. There's a lot of people using it. So that gives you an idea of the scope of flame graphs, and I may have mentioned one of those products that you're already using. So CPU profiling. Here I'll explain an introduction to flame graphs and how they work. Here's a stack trace from Java. I'm sure a lot of you have seen this kind of thing a lot. That's a single stack trace, so I can walk from what's running on CPU to the parent, grandparent, and so on. With CPU profiling, the word profiling doesn't really mean a specific thing. It means painting a picture of a target or a person. In computer performance, it typically means we will record stacks at a timed interval. But it can mean tracing the execution of software. So I've seen some profilers that will trace all function calls and then assemble that into a profile. I try not to do that because it can be CPU expensive to trace all of your method calls or function calls. I prefer this is commonly what a profiler will implement, where every 10 milliseconds or 100 milliseconds or whatever it is, it will take a stack sample. You'll often see these profilers. They take stack samples at 99 hertz or 49 hertz or 997 hertz or 103 hertz or some weird number. The reason for that is we don't like taking stack samples at 100 hertz or samples per second or 10 or 1,000 because those round numbers can incur lockstep sampling with the running software. So you have a background thread that's pulling something every 10 milliseconds or doing some sort of code logic at a regular interval. If the profile sampler is started at just the wrong time, it will always catch that interval or always miss it. And so That's why we try to do 99 hertz or 103. Some profilers actually do a jitter, so it will add and subtract some time each time it takes a sample. CPU profiles don't see what's going on when you're off CPU, so you're blocked, unless it's a wall-time profiler. Over time, I can draw it like this. I've got stack samples. There's the stack depth on the y-axis. So on the first one, A called B, called C, called D, called E. I can draw frames on them. That's a bit hard to really see. It just looks like a lot of text and boxes. One thing I found is if you just randomly assign colors to function names and then stick with it, it helps reveal patterns. And so when I first look at function names, I say A is going to get yellow, B is going to get orange, C is going to get red, and so on. And then I stick with that later on. You'll start to visually see things more easily than just trying to read the text. Your eye just has to look at colors. So far, so good. Let's try this with a real-world profile. That's what it looks like. Awesome, ship it. So this doesn't actually work that well. So I've called it a hair graph, and this is a real workload. The problem is on multi-threaded programs, things are changing so often that at a long time interval, it's just a big mess. So we can be a bit smarter. If previously we saw A was all the way across the x-axis, instead of always drawing it as a box, why don't we merge that frame and then just draw A once? So that's what we can do. We can, if it's adjacent, it's like a terrible version of Tetris, we can just keep joining them together. It looks like this. It's improved. We can start to see some of the things. But we can still go better. If instead of having time on the x-axis, we sort by the alphabet, and we do an alphabet sort from bottom to top, it groups things together much better. And so you can see now I've got a line of Ds and a line of Cs and a line of Bs. When I merge those frames together, oh, now that's merging is much more effective now. Whoa! And there's the flame graph. And I've just explained what flame graphs are. It is the alphabet is on the x-axis, and I sort all of these stacks by the alphabet and then merge those frames together. And when I showed my colleague Isaac, and I said, look, it's the alphabet, and we're looking at the whole population, that's the bit he thought was weird, because everyone expects time to be on the x-axis whenever you do this kind of plot. But it just took him a few days of playing with it to realize, no, this is great, because the alternate is not really readable. That's a flame graph. I was at Netflix. When I first got it working for Java, my colleague, Amar, who just sits across from me, I was showing my teams, like, look, I got it working for Java for the first time, mixed mode flame graphs. You can go in and out of the kernel. Amar says, oh, it'd be great if you could change the color so Java is a different color to C and C++. He barely sat down at his desk. When I looked at it, I'm like, well, Java has these slashes and C++ has colons, so I'll just do a regular expression. And if it has a slash, I'll color it green, and if it has a colon, I'll color it yellow. So I called Amar back like 2 minutes later and said, done, colors. So very simple. Regular expressions can get abused a lot. I worked with a guy whose name was Guy who hated regular expressions. He actually created regexlicense.com because his theory was you needed a license to be able to use regular expressions. So anyway, very quick hack. Now I'll replay it, but this time using the colored version. So there was time columns where I'm doing the stack samples. Everything's a column over time. Now I start to merge things together if it's the same frame adjacent. This is also known as a flame chart. I'll get to that. And then I just reshuffle everything to maximize merging by using the alphabet. But you could use a different algorithm. It doesn't have to be the alphabet. Flame graph. The origin was I mentioned it briefly. It was a performance issue where on Monday we had this customer found that the competitive system ran faster than our system, and our system consumed more CPU. And as a performance engineer, it's like, well, it's a CPU issue. I'll run the profilers. Often it's the most frequent stack. So I ran a profiler on one system, was dtrace, and so I'm profiling way too fast, 997 hertz. I mean, the stack traces were not that deep, so I got away with it. And I started looking, and the output of this shows if frequency counts the stack trace. So the last stack trace appeared 5,000 times, and that one appeared 4,800 times, and so on. Great. So I just look at the most frequent stack trace, and I see if that's the issue, and then I go to the next most frequent, and so on. The full output was this, visualized, and so the most frequent stacks are here. And by Wednesday, I'd already gone through the most frequent stacks and not solved the issue. I don't have a maybe I do somewhere. I don't have the visualization, but I had the same profile from the competitor system, which was Linux, and I was using perf. And it also had this just wall of text that I had to sort through. And I was trying to find the one difference between these two profiles. In a way, I was looking for one needle across two haystacks. As it turns out, it was a really important issue, and so there's a lot of pressure on me in the office to be working on it. And I didn't feel like I could be goofing around with visualizations while this was so important. So I actually did this out of hours. It was a spare time project. And also I had a previous experience where a colleague had goofed around with visualizations that didn't work out, and there was pressure not to waste time on that. So flame graphs didn't come from an environment where I was encouraged to do this. Quite the opposite. I was encouraged not to play around with visualizations. But I'd come up with latency heat maps before to visualize the latency histograms, and I really felt that, there just has to be a better way to do this. That's the flame graph for the same profile data that I came up with. And then straight away, it's like, we're in MySQL do select, and we're doing a join, and we're spending all our time there when we shouldn't be. There's the problem. So instead of looking for a needle in a haystack, it turned it into this giant pink pool noodle that was sticking out of the haystack. And not so much of an exciting story. It's like, there's the issue. It's right there. So as an example, what that looks like on Linux perf profiling, it aggregates things a bit better than the other profiler I was using, so it does this hierarchy, a call tree summary, but that's still the output of a perf run. It's too much data. And there's an example flame graph. The inspiration was from a colleague at Sun Microsystems, Neil Akant, came up with function call graph in Ruby, and this was over time. And Neil was inspired by another colleague of mine from Sun Microsystems, Rock Bourbonnais, who I work with a lot, his call stack analyzer. And Rock would tell me to keep using his call stack analyzer. Like, you should use this, it's really awesome. I have yet to find it, it's so many years ago, I've yet to find a screenshot of it. But it looks similar to this. And that was inspired by an earlier tool called ftrace. So there had already been a lot of work in doing function flow over time. This was different to flame graphs, though, because the x-axis here is time, and this only worked because you traced going in and out of all of the functions. So if you gave a profile to these visualizations, it didn't work because a sample-based profile has gaps in between those samples. So the flame graph summary, how would I summarize it on a single slide? X-axis is the population, alphabet sort. Y-axis is the stack depth. The color, I went with random warm colors. I thought this was too many colors, so I just changed it to just be warm ones. And that made it much easier. I also put, in my original version of flame graphs, I put all of this in the source code because I like to thank where these ideas come from. My original implementation was Perl, but there's lots of other ones, and I went through a bunch at the start. How do you interpret them? Here's an example. If you look over the top edge, that shows who is running on CPU and by how much. By how much, you just look at the width and you compare line lengths. Comparing line lengths has been evaluated as an easy visual task. There's a variation on flame graphs that uses polar coordinates, and it turns them into these radial diagrams or sunburst diagrams, which I find a bit harder to interpret. This is great because everything's a rectangle, you get to put the function name in, you're just doing line length visual comparisons. So I look at this, G is on CPU the most because it's the top edge that's the biggest, followed by I. When you read down, you see the ancestry. G was called by F, was called by D, was called by C, and so on. The widths are proportional to the presence in the samples. I can look down in the stack and see that B and its children looks like about 3 times more than H and its children. And the colors, I randomize them to differentiate frames. Some people do implementations where they don't randomize the colors, and it can be a little hard to see adjacent towers. I ended up using hues, my colleague suggested that, so that we can see different types of code. Some flame graph tips and tricks. People show me flame graphs all the time. Brennan, check this out. I always start at the bottom frame and look at how many samples. It's about time I actually showed you a flame graph. Let me switch to one. So here's a flame graph. I said I start at the bottom frame. If I mouse over the bottom frame, it says 2,963 samples, OK. If that said 17 samples, what might I conclude? I might conclude that was an idle system. And this would happen at Netflix a lot, where you have an instance or an ASG that's melting down, an instance that's bad, it's using too much CPU, and then it would get killed and taken out of discovery, the load balancer would send traffic elsewhere. And so by the time people were looking at it and collecting flame graphs, the system was no longer running the workload. It was idle. So there's no, maybe I need to visually put it in there somewhere. But I start with the bottom, and if I see there's only a handful of samples, there's only like 12 samples or 24 samples, it's like, this sounds like an idle system, so it's not going to be very, very interesting. You want to see lots of samples. And you can just do the math. So if I'm sampling at 49 hertz on a 64 CPU machine for a 30-second flame graph, there should be thousands and thousands of samples. Flame graphs, you can also zoom in. So I can zoom into this. And then I can mouse over, and it gives me details. File name lookup was 32 samples, 1.08% on CPU. And I can do a search. So let me just zoom back out again, look for file name. That was only there, that's boring. Look for built-in. And another thing I like to do is, if you do a search, I show how much of the profile was matched. So I just searched for built-in, and it said built-in was in 45% of the profile. So I'm not including it twice or 3 times because it's in those deeper stacks. This is useful because as a performance engineer or developer, you need to know quickly what is the magnitude of the issue. Should I solve this issue or that issue? And so you quickly want to be able to add it all up. So that's why I can search for all sorts of things, search for word shell. Here's a different one. Let's search for Netty. This one has the colors. So Netty's 94% of the profile. Let's search for the kernel code. Let's search for TCP. OK, so there's TCP. TCP was present in 26% of the frames. And then, of course, now that I've found it, I can then zoom in and go into the finer details as to why. Off-CPU time, such as I/O and locks, is not present. But their initialization CPU frames may be. And so you may see what turns out to be, in a way, breadcrumbs of their existence. So you see, like, oh, look, we are doing a lot of time in the files, like 5% of time in the file system and initializing block I/O. When you see that in a CPU flame graph, you've got to think, gee, if I'm spending 5% of my cycles initializing disk I/O, I may be spending 50% of my time waiting on disk I/O because I can't see that blocked time. We can do enough CPU flame graph to see it, which I'll cover later. There are some tiny CPU code paths that might be missing. It depends on your system and the profiler you're using and all of that. If you're on the cloud, then you may not be able to see hypervisor. We shouldn't be able to see hypervisor time from the guest. You may not be able to see kernel code paths that disable interrupts. Doing an interrupt-based profile. Hardware-based profiles can see more. This is a detail of the profiler and the target. People send me this stuff from time to time saying, Brendan, please fix it. And it's like, the flame graph visualizes the profiler. You need to fix the profiler to see more, and then the flame graph will visualize it. Another tip and trick, if there's still too much hair at the top of the flame graph, you can reverse the polarity of the neutron flow and merge at the top instead, a leaf merge. That's not actually what it's called, but anyway, leaf merge. So this was a profile I had at Netflix where you can see it's hair. It's like, okay, that's not terribly great. But what if they're all calling the same function, right? What if this is the same function at the top of all of those strands of hair? And so all I do here is I flip it and I merge at the top instead. And I see that, oh yeah, we're all in Zen hypervisor, native flush TLB, and we're doing handle do NUMA page. Great, and so this was actually a NUMA issue on this particular build of Ubuntu, and I was able to figure it out. My original flame graph implementation let you do this by doing minus inverted and reverse. I did this so that I could merge at the top instead of the bottom. A lot of people actually like to merge at the top, flip the flame graph because they prefer it upside down. I'll get to that in a sec. Flame graph interactivity, if I was to mention some essentials, I just did a quick demo. So you can mouse over for frame info, click to zoom, and search. Control F. There's various other things that are nice to have. So if you're working on a flame graph implementation, or if you are buying a flame graph implementation from a vendor, there's plenty of open source versions out there, but some of you may already have it as part of a commercial product. I like to have merge control so you can change whether you're merging from the root or the leaf, or maybe you want to merge around the middle frames. Maybe the middle frames are your developer's frames. This is my code. Let's merge around that, and then that's my perspective of the world. Which direction we have the flame graph? So you can just flip it, so it's an icicle graph instead. Have a toggle. Flame chart, so you're doing it over time, even though I just showed some visualizations where it didn't work. Sometimes it does work, especially if it's single-threaded. Can searches, collapse filters, and links to code. So you can look at a frame and go to a code link. Which way up? So I did have inverted for an icicle graph. It's fine, whichever way you want. I think it's kind of an Endian argument, which end of a boiled egg to break. Although there is slight advantages for the icicle graph if your UI begins showing at the top, because some very tall flame graphs, when it begins at the top, you just see strands to start with, and you have to hit page down. And so if I look at this one's a bit tall, if I reload it, it may start there, and then I need to scroll down to see it. And so it's a legitimate reason why you may want to have it upside down, so when you load it, the roots of the flame graph are visible. I noticed that Microsoft, in their Visual Studio, they've got a button, so you can just flip the flame graph. So you just let the end user choose which way they want it. Differential flame graphs are another type. And here I'm now going to use the color for a dimension of information. So red, I'm showing more samples, and blue, less samples when you're comparing, say, one software version to another, or one system to another that's running the same code. The intensity is the degree of difference. And so I can look through this and I can say, well, red is where there's more samples, so we've grown, and blue is where we've shrunk. There's another project for this, flame graph diff. With Netflix, we have this for Flame Commander. You've got to be careful about elided. It's great. There's a few tricks about differential flame graphs. One is inlining. Java can inline differently from one run to the next. And so when you're trying to do the differential flame graph, if it's the native frames after inlining, they can be completely different, and so the differential doesn't work. And so you have to do the differential on uninlined, which is just one of the gotchas that you'll run into if you do this. Another gotcha is sometimes code just vanishes from the second profile. So if I'm comparing the difference from version 1 and version 2 of software, and like there was a tower in version 1 that's now gone, it's not visible in version 2, so sometimes you need to have an extra flame graph of like, this is the code that's gone, that's vanished. Now I mentioned there's a few implementations of differential flame graphs. This is actually how I do differential flame graphs a lot. I have them in different tabs of my browser from system A and B, and I just flip between them like this. Oh, what's different about these two flame graphs? It's this bit over here. That's actually how I do it. So you can just do that. You just load them up in one and the other, and you just flick between them. Done. you can do this in software. That's fine. That's fine too. Just to mention system CPU profilers, on Linux, perf is the one that comes with Linux, perf events. eBPF is more efficient. It can do kernel aggregations, and there's a tool that I initially wrote BCC profile for that. Windows has it in XPerf and WPA, and Visual Studio now. OS X instruments, there's ways to do it, and there's many more. Use system profilers wherever possible, not the runtime profilers. So if you go to, like, in the world of Java, there's a lot of profilers based on JVM-TI, and that only shows you your Java frames, and so you don't see the rest of the system, the kernel and the amount of CPU time in garbage collection and other bits and pieces. In the slides, which I said are online, I do have some instructions for Linux, for creating them at Linux. In fact, it's so easy now that perf script has flame graph as a subcommand that Andreas and Red Hat added. You can just run perf script flame graph and you get it. Cool. That's using eBPF, all open source tools. You can create it using my old Perl. Yes, you can install my Perl software in your systems, keep Perl alive. I really don't care. You can also just rewrite it in whatever language you want. You don't have to use my Perl code. And then generate the SVG. And I've got some other instructions in there as well. So the old-fashioned way was using perf record on older Linux. Just to visually explain why I care about eBPF, here's how we were doing it. Lots of steps involved writing samples to the file system in perf.data, and then rereading that data and processing it, and then sticking it out. With eBPF, we just summarize it in kernel space and then stick out the small summary to flamegraph.pl to visualize. Much more efficient. A lot of you are not even going to touch the command line versions. You're just going to use GUIs. That's fine. It's the case at Netflix, so engineers solve a lot of issues from the self-service UIs. And at Netflix, I worked on lots. Netflix Vector, which we retired, Flamescope I'll cover later, and Continuous Profiler. But there's other open source versions as well. There's Granular G Profiler, Eclipse Trace Compass, Grafana just added flame graphs, lots and lots. Flame charts I mentioned once. Flame charts were inspired by flame graphs. So there was my post on flame graphs, and then someone said, let's add flame charts to the dev tools, the browser dev tools for Chrome. And that, well, let's add flame graphs. But Google did not implement it as the alphabet on the x-axis. They implemented it as time on the x-axis. So either they got it wrong or they got it right. That's what it looks like today, and you've probably used this. This is not as hairy as my earlier examples, because with JavaScript, the runtime in the kernel, V8 and whatever implementation, they're typically single-threaded. And so you don't, with a multi-threaded app like back-end servers, you just can't put all those samples on one timeline because it's just a mess. But if it's a single-threaded app, you can sort of get away with it. So perhaps it was deliberate. They did not call it flame graphs. They called it flame charts, which is convenient because now flame charts are time on the x-axis and graphs is alphabet. They should add a way to do both. Firefox's profiler, you can do both. So you can do flame graphs and flame charts, two views of the same data, which is great. That's what I recommend. So flame charts, x-axis is time and graphs, x-axis is the population. I want to briefly go through some challenges with flame graphs so that you're aware. Broken stack traces are super common. So here I'm running perf record and like, my application only has a stack depth of 2 with this crazy number. It's broken, happens all the time. This is what it looks like as a flame graph. Here's my Java frames. Oh, they're just this green grass at the bottom. How do we fix it? We can turn on frame pointers. A very common issue is that a long time ago, around 15 years ago, frame pointers were the way a system will walk stack traces, and the GCC compiler engineers decided to reuse the frame pointer register as an extra general purpose register because it improved performance on i386, on 32-bit systems that had a limited number of registers. It didn't matter so much for 64-bit systems, but we're stuck with the change so far, and we've been trying to, speaking of changes, and we've been trying to undo it. Oh yeah, absolutely, I want to update my computer in the middle of a presentation. That'll be great. So frame pointer based is this change that happened in GCC a long time ago. I very recently, like the last 7 days, I've still been pushing on getting that fixed so that you don't have to do the work. But a lot of sites like Netflix and Facebook and others, they just recompile all their software with frame pointers. Problem solved. So frame pointers are always there. Frame pointers are a way to do stack walking. There's other ways to do stack walking, like dwarf, debug info. It's not great for, it's good for debuggers, but not great for profilers or real-time things. JITs can provide runtime walkers. They should, because they need to for exceptions, stack traces, and there might be a way to hook into that. Intel has a feature called last branch record to do it in hardware, although it has a limit, may only reach 32 frames. And emerging technologies, add-on walkers using eBPF. So I at Netflix did the original work to fix the frame pointers in the JVM, and Oracle took my work and included it and rewrote it and included it as preserve frame pointer. So when you run the JVM with that option, the stack traces are now fixed, which is great. The performance impact should be very small. It should be 0.1%. There may be an exception though, so do test and see what it looks like. There's fixed flame graphs. Fixed, we don't have symbols. Fixing symbols for compiled software, there might be a debug sim package on Linux, or you recompile it with the right options. For Java and Node.js and other runtimes on Linux, perf likes to use a supplemental file. So I'm running perf script. It's trying to open this thing called temp perf whatever.map. It's like, oh, I can't find it continuing without symbols. There's software on GitHub that will create these supplemental files. So there's Java's perfmap agent that will create that symbol file, and then when perf runs, it can navigate the symbol table for runtimes. You have to keep refreshing it though, because the C2 compiler doesn't stop. Although I wish I had a way to stop it. Stop compiling so I can do things. Fixed. Now we can see Java frames. When I joined Netflix, Java profiling actually looked like this. So Netflix was doing flame graphs using a JVM TI profiler, so you could just see the Java bits, and then using a system profiler to look at the remaining bits. And then in your head, you were trying to connect the dots. But by 2018, I got it all fixed. And I talked about this at YOW 2018. So now the Java frames are on top of the system frames. You can see going in and out of Java and back into the kernel and so on. That's a mixed mode flame graph. Just an example of why that's useful. This is one that a developer brought to me and said, well, I've got a performance issue. I pulled up the flame graph and went, whoa, you are calling exceptions. Like, is there an error in the code, exception handling? And the developer had a look and went, oh, someone needed some system property, and so they just threw an exception to get it. And like that was, because it has to work stack traces and do all this system-y stuff, it was consuming a lot of time that's not visible in the standard Java profilers. So it just stood out straight away in the mixed mode flame graph, and they're like, oh yeah, we can just cache that property, or we don't need it, or we just eliminate unnecessary work. Various other issues to be aware of: JIT symbol churn, so that snapshot can change over time. And so there is a newer feature in perf where it can do time-stamped symbol logs of Java. Containers bring all sorts of issues. Solve one issue and create like 10 more. So containers, like, are you reading the files from the right namespace? It should now work because there were a bunch of changes to this. And stack depth limits. We had one microservice at Netflix that would frequently run to over 1,000 frames deep. And Linux had a 127 frame limit on doing profiling. And so Arnaldo Carvalho de Mello fixed that for us. And so now there's a sysctl, so you can increase the stack limit. Inlining I mentioned before. Inlining can be a problem, especially for differentials. But I've talked a lot about Java, but every runtime can have its own special stack or symbol instructions that you need to look into. So whether it's Node.js or Python or Ruby, try an internet search and try and sort by date to find it the latest. The final topic is advanced flame graphs. Now you've got CPU flame graphs, you've got them working. What else can we do? Flame graphs can visualize any stack trace collection, or really any hierarchical data. Here I've drawn the Linux events that you can measure. So any of these, I can do a stack trace I can do a flame graph for disk I/O, network I/O, hardware events like cache misses and so on. Some of the flame graphs people are using do memory allocation flame graphs. I like to do it this way instead, page faults. If you do memory allocation flame graphs by tracing the allocation function, that can happen 1 million times a second or 10 million times a second. And so it can become CPU expensive to gather all of those stack traces. Page faults happen when your RSS grows, your resident set size. And so that's a very infrequent activity. It might happen 5 times a minute. And so it gives you a coarse idea of why you might have a memory leak or memory growth. But what's nice about it is the overhead is basically 0. So a page fault flame graph, like if you're looking at top, it shows you why that res column is growing. And it's like, oh, here's my code of why it's growing. You have to collect it for a long time, though, at least 2 minutes. You can't do any memory. There I've drawn a diagram of how memory allocation works on demand-based operating systems, which most are these days. So you can trace the allocated functions. They can be high overhead. That's why I like to go into the heap and do page faults when we're going into the MMU, because the operating system lies to applications and says, yeah, sure, I've mallocked that memory, but it hasn't, only when you later do loads and stores, or stores to start with, you'll fault through the memory management unit. And so that's an indication of growth. You could do disk I/O flame graphs, but do pick there's a lot of disk events that are not synchronous with the code. So on completions, they aren't. So you need to pick when you're issuing disk I/O. Context switches, when you're blocking and going off CPU, that can be useful. At one point, I did it to look at the difference between RxNetty and Tomcat, so epoll versus syspol. TCP events has another issue about asynchronous, but you can do TCP sends as a flame graph. I've got the instructions in the slides, so you can see why I'm calling networking. Cache misses, I can do hardware-style things. You do need this. If you're on Intel, you need PEBs for IP accuracy, precise event-based sampling. CPI flame graph, I'm taking the differential palette, but I'm showing you where your CPU hot versus memory hot using red and blue. And then off-CPU flame graph, which solves everything that's not CPU time. CPU time is in pink, and off-CPU time is in blue. There's an example off-CPU flame graph. I changed the colors just to make that point. And if you zoom in this case, I've got the tar disk archiver. I can see how much time am I reading from disk, file reading from disk, doing fstat, and other things. This is a great complement to CPU profiling as you get to the bottom of all your performance issues. See everything if you do both, CPU and off-CPU flame graphs. there I did them both in one flame graph, which sort of works. Off-CPU flame graphs can dominate because you have so much time waiting. There is another advanced one I created called off-wait time flame graphs, because often if you do an off-CPU flame graph, you find you're blocked on a lock or you're blocked on polling. It's like that's not enough information to understand what's wrong. You need to know the waker thread and its stack trace. Why was that lock held for so long that I was blocked? And so in this example, I have a waker stack and I paste it on top to explain it. And you can keep going all the way to metal. So I can chain them and I can do all the waker stacks that led to that path blocking. This is still a work in progress though, because it's a lot of overhead to capture all of the stack traces. Flame scope, I did mention earlier, is another advanced thing. That's where I print a sub-second offset heap map. So you can, this paints samples from bottom to top. 1 second is a column. And the color depth is how many samples are in that second. That way you can see issues of variations and perturbations within a second. And you can highlight them, and it'll give you a flame graph just for that range. And so we open sourced that, but it's another advanced thing you should be using. Once you've got flame graphs working, now you want to, the problem with flame graphs is they can be, say, a 30-second average. You want to know what happened within the second or fractions of a second. And so I found that was quite an effective approach. And here's a flame graph example where there's all these patterns. So this diagonal line is from when you have a thread that's waking up every second and doing a little bit of work, but then it's blocking for an entire second, and so you get that offset. And then I've got these stripes that are appearing. That's probably garbage collection. I can see these horizontal lines from threads that are waking up and doing little work, or they're using a different timer, so they're always waking up at the same offset. So that's some advanced flame graphs. It's an agenda recap. I went through implementation, CPU flame graphs, some challenges, and some ideas for future work. You can look at the slides on how to interpret CPU flame graphs, and hopefully you've learned that, understand some challenges, and eBPF is necessary for these advanced flame graphs for efficiency. The slides has lots of links and references, and thank you. We have some time for questions.
Does anyone have any questions? There's one.
Have you seen many examples of teams incorporating flame graphs into their continuous integration build processes to be continuously showing a current flame graph for a given branch of the system?
Yes, absolutely. So for continuous integration, Jenkins and other things, it's great because you'll have regressions, and then you straight away have the flame graph to explain the regressions. Also, companies have, say, automated micro-benchmarking, so it will do a benchmark every night of this code base. Again, you include a flame graph with it, because when you have the difference, the first thing you want to see is the flame graph. It's like, why do I have the difference? And now I know I have a difference. Why do I have a difference? Absolutely should include it. If you're managing that stuff, there's heaps of open source options, or there's commercial options. Go for it.
Are there any good tricks for recognizing whether you have the sort of synchronous problem? You know, you mentioned 101 hertz, 99 hertz. Recognizing that problem?
Recognizing the lockstep sampling issue, I don't know. I haven't really spent much time on it, so maybe you can come up with something if you think you have it. I never do like 100 hertz sampling. I'm always doing 99 hertz sampling. Flame scope is great because with flame scope you can see there are some periodic things, and you can control how many rows you have. So these horizontal lines, maybe it's multiple threads, or maybe a thread's waking up 10 times a second, and there's a line for each wake up. And so that might be, I would use this as an approach to try and look for periodic activity.
Thank you, Brendan. That's all we have time for. Thanks very much for that talk, Brendan, today. And Brendan's available in the exhibition area through the day and probably tomorrow as well. Thanks again to Brendan.